Maybe I should start. So I will share my screen. कैसा? ಇಲ್ಲ ಶುರು Okay, let me start. So, this is where we kind of left off last time. So, I was just using the simple DNN example to illustrate some of the things that how to, what are the steps, the main steps in verifying, using logic, doing formal verification to verify any kind of artifact. They could be either software or something else. The first step is to model the behavior. In this case, our artifact is a DNN, and then model the expected outcome. That is usually called the property of interest. That you will have to specify in the logic of the prover, and then you formulate a verification condition that is appropriate, which, when checked, guarantees that the property holds in the way that you intend to have it. Okay, decide now. In a lot of cases, the what you want to prove is that some expected behavior at the output holds for all inputs that satisfy a certain assumption of the kind that Diganta showed in his. Yes. Hello? Is there a question? Okay. So in that case, what you want to check, the property that you want to check is you want to check for all inputs where the condition that you want to check using the theorem prover like Z3 would be validity, that under the input assumption, and given that the DNN is modeled in a certain way, that the output is defined as as per the model of the DNN, then the property holds good. Now, then we started last time discussing in what sense this formula, which is defined as the predicate DNN here on the right side, exactly in what sense does it actually model the behavior? So that's where we stopped. I'll get into that. But here, I mean, I want to talk about, spend a little bit time on, showing that the validity may not, is not necessarily always the kind of thing that you want to express your verification condition in. So what the kind of condition that you want to check will depend on what the behavior that you want that is of interest. And also the specification itself, depending upon the property you want to verify, writing the specification and formulating it, can be a complex process. First, I want to, spend a little bit of time. Now, here, I have listed 4 properties. Okay, the first one is very much like what I just now stated. So, you want to prove that if the input is, for every input, if the input is non-negative, then the DNN output is always equal to the input. Okay, so then it can be expressed as a universally quantified property. That is, for all values V1 on inputs and output V1, 3 variables denoting the input and the output value, if some input condition holds good and V13 is the output for the input V11 as per the way that the model has defined the DNN, then you want V11 to be equal to V13. And since you want to prove, you want this condition to hold for all values, then obviously the verification condition is to check the validity of it, which is expressed as an unsat of the negation of that. And that's what I'm doing here. But there could be another property like you can even query if you might be interested in asking the question if there exists an input for which DNN output is not equal to its to its input, which is actually the case here for this DNN. Then your specification is not a universally quantified thing. It is more like an exists. You're asking the question if there exists an input-output pair, for which if they are, assuming they are related as per the DNN model behavior, if you want to check if V11 is not equal to V13. In that case, your query to your theorem prover would be a satisfiability query. Okay, because an existence of some instance of V1 and V3 is expressed as a SAT query. Okay. Moving on, it could be even more complex, behavior that you want to query and check. For example, you might be interested in asking the question, if there is a possible contiguous range of values for the inputs for which the DNN output is equal to negation of its input, okay, or something like that. Then you see your query gets more complicated. So you want to, this can be expressed by this formula, which uses quantifier alternation, okay? Let me see. So I am specifically looking at, people who have not had logic course to see if they have any problem in reading this query. Is Pradika and Harsh here?
Yeah, I'm trying to make sense of
Yeah,
it.
and you have to, you have to ask questions. That's why I'm taking it a little bit slow, at least for the this class and the next one. So please feel free to ask, interrupt me and ask any questions if you don't, if you have trouble understanding what I'm trying to convey. Okay, so this is ask if here's then so you're interested in seeing if there exists some D1 and D2, okay, such that for all input-output pairs, if V11 is in between, is within that range, inclusive of the bounds. And see, there is always this DNN predicate will be there because you want to assume that V13, the value of V13 is related as per the definition of D1 DNN, modeled by that predicate DNN. Then it's asking the question if V13 is equal to minus the negation of V11. The question I have is, can this be checked in Z3? I don't know if yes, the answer is yes. You can actually, Z3 does handle limited form of quantifier alternation of this kind, okay? If I start a predicate calculus is undecidable in general, and one of the source of undecidability comes from the quantification there. Okay, and nested quantification, even when nested, and the fact that the domain here, if indeed you're asking this question over all reals, and reals are, and it's an infinite domain, and then you have this kind of a query, and this, yeah. So in general, it is undecidable, but there are fragments of first-order predicate logic with quantifiers over infinite domains, for which this, checking this is decidable. So you could, Z3 does implement certain decision procedures to check these kinds of queries with under certain restrictions. Okay. Even when it does, this problem of checking in the presence of quantifiers alternation is complexity-wise is a very hard problem. And therefore, even when your instance is decidable, Z3 may not return return successfully the result in any reasonable time. But it would be interesting for you to type this query for that simple DNN example that I showed earlier, and then see if what Z3 does. Okay. Now, I have another question. Can this query be checked with repeated? As you know, see, in the case of 1 and 2, I expressed it. There was only one quantifier there, okay, which was at the outermost level. So there, if there's only one quantifier at the outermost level, if it is a for all quantifier, then your check is validity, and then it can be expressed as a simple unsat check, as we did in the case of 1 property 1. In the case of 2, it can be expressed simply as a simple SAT query. The question I'm saying is, you see, you can either type this thing up to Z3 and then see what it does, or you can make an algorithm to check, to generate, to see if you could, if there is some D1 and D2, that satisfies the formula F3 by making repeated calls. Okay. So under some restrictions, what Z3 does internally when you type this thing up is, something similar. Okay. You can imagine, so for example, if your search of D1 and D2 is within some bounds if you're looking at it. If you want to do in general, your algorithm can be difficult. But if I, modify this question into asking if there exists a D1 and D2 within a certain bound, you may be able to devise a search algorithm, which makes repeated search to check if there exists pairs of values between those bounds for D1 and D2. And then you can reduce this into a number of unsat calls, because for each value that you want to check, your call is a for all check. Okay, so there is a way to write a program, okay, to reduce um, uh, checking this query into making repeated SAT calls. Okay, and that is what one of the problems in your exercise, the logic exercise, the updated logic exercise that I have included as a problem, and I want you to try. We can get even a little bit even more ambitious, okay? And that's what is done in property 4. And that is asking the question, if there is, you may not be here, the first question, here I'm asking if there exists some value D1 and D2, okay? The bounds. Here I'm asking, making the search even a little bit more complicated. I'm asking if there are some maximal contiguous range of bounds, D1 and D2, such that for every value within that range, the DNN output is a negation of its input. Okay. This once again needs a quantifier alternation of this kind, okay, that I showed here. And, the question I'm asking once again as an exercise problem in the updated assignment is for you to first specify this as a formula using quantifiers. Okay? And then, devise an algorithm which reduces checking and generating values for D1 and D2 as a repeated in terms of making repeated calls, SAT or unsat calls to Z3. Okay, so that's what. Any questions here? Okay, as to making the constructing property specification. Okay, the key takeaway here is that sometimes the property that you want to specify may not be simple, expressible by simple SAT and unsat call. And that happens whenever, and because it may need for you to have several quantifiers. In that case, also in some situations, you can reduce that problem into repeated problem by repeatedly making multiple calls to Z3. And how you can do that is by writing a program. So now is a good time, if you don't have any questions, for me um, to back to the assignment. Okay, so let me ask a question. So just a moment. Yeah. So how many of you have started working on the assignment? I know the deadline that I had announced, at least for some part of the questions that I wanted you to solve, is already over. And the reason I had an aggressive deadline there was because I wanted to force some of the people who had not had a logic background, formal logic background, to start working on it. So I'm asking if there is anyone that having any problems, and you will have to speak out, okay? And the first part is quite simple, okay, or at least the part A. And what I have added are this section, part 3 is where I've modified, and that part is something that is involving proving some properties that I just now listed for the DNN, that simple DNN that I've showed. Okay, 1, 2, 3, I've already specified the properties. It is 4 where you have to specify the property and then devise an algorithm for doing it. And implementing, I'm asking you also to implement this algorithm using the Python interface for Z3. Okay, because when you want to make your own strategy to use a prover like Z3, you need to, the best way to do, the only way you can do it is using its interface API and embedding it inside a program. Now, that is what, and I know you haven't seen this, the way I introduced Z3 was through a GUI interface. For this, you need to use the Python interface. And I've asked, Shauriam and Avik to introduce you to the Python interface, how to use that inside a program in one of the tutorials, upcoming tutorials, as I had indicated in earlier in the introduction lecture. I'm reserving Fridays, a session on Friday as a tutorial, and the timing for that slot will be worked out with you by Shauriam and Avik. And attending those tutorial sessions are optional. But if you're having doubts about any some of the things discussed in the class, or things like this where you need certain additional material for about some of the tools that we introduce, starting with as basic thing as installing those tools and or clearing doubts about how to use them, including for some of the harder parts of for solving the problem on assignments. In this case, for example, Python interface, I'm not going to be introducing in regular class, and it'll be only introduced there in the tutorial. And the tutorial, those extra sessions are meant for that. Okay, and that's what I wanted to emphasize here. I'll make and there are a few more problems here, and I'll make a new deadline for the updated assignment. And this assignment is for everyone. Okay, the original one where I had asked, I guess, part 1 and to be solved part 1, and this part 2, I guess, I had indicated was to get you to start doing it for your benefit to get acquainted with Z3. But now this assignment is for everyone. I want everyone, even those that have had logic background, to attempt, to complete it. Okay. So any questions on about this, about the assignment or the tutorial? Okay. Let me see who all are there. Okay. Okay. Uh, then I'll go back to, okay. So now I've talked a little bit about the variations on the different kinds of properties that we want to verify. Now we'll get back to discussing, you know, why this is, the way that I've defined DNN, okay, the predicate DNN, why that is indeed a model of the thing. Okay, first of all, I mean, I started last time by converting this DNN into a simple sequential program, okay? And I made the observation that a DNN, simple DNN of this kind is, okay, just give me a moment. I'm going to move to a different room. Yeah. Um, okay, sorry. Yeah, and why is it that I'm, firstly, and I want to introduce for you to, program verification. But even though the DNN, as when viewed as a program, is a very restricted kind of program, it has no branches. I mean, it has branches, but no loops. And every variable here is assigned at most once. But there are other models, not only variations of DNN, as well as other machine learning models where the uh, where the behavior could be as complex as a general purpose program. Here, there is a variation that people have looked at, variation of DNN called recurrent neural networks, which, unlike an ordinary DNN, which is actually people have used it for language translation, learning language translation, and as one of the applications, which has a memory in it. Okay. So, for example, you can, some nodes in your DNN can have memory. Okay, they can remember the value. Remember the value that. So they work. I mean, these are applications in which the DNN processes a whole sequence of tokens and maybe converts them into another. Language translation there, it needs to have some history component. And so there are nodes that remember the previous values that have encountered, and the next value, the output that it produces, is a function of the remembered value. So so this is very much like a program with loop where some of the node variables denoting the node output are assigned multiple times. And for that reason, it does make sense. Even otherwise, even when your interest is focused, may not be on software verification, to look at program verification in general. And that is the direction that I'm going towards. And so this is a step towards that. Okay. So now let me introduce you to one, and the logic, very popular logic that was introduced, a special purpose logic that was introduced by a computer scientist called Hoare, Tony Hoare, and the logic is named after him. That logic was specifically designed for constructing and modeling behavior of programs and constructing proofs about program. So I want to introduce some of the basic concepts in that logic, to which will also explain why the way that we are modeling even this simple DNN is correct in some sense, is sound in some sense. The first thing there is the concept of the strongest post condition. Okay. So, and that asks the question. So, for example, what is, and here, after each assignment statement that I've here, I'm asking the question, what is it that you can actually make a statement about? The state of the values, the conditions that have to hold good for the variables that have been assigned by that assignment statement. Okay. So in this case, for example, so V21B is assigned V11. So what is the strongest statement that you can make? You can definitely say that V21B is equal to V11, correct? So, so the idea is, and that is what is called the strongest post condition. What is it that you can assert about, after each of those statements? And that's exactly what is, in this case, it is quite simple because they are all fresh variables. Therefore, here, for example, you can make the assertion that V2 1B is always equal to V11. Similarly, V22B at P2, V22B is equal to minus V11. And here there is a branch. So for each of those branches, you can make certain assertions about what happens at the, if that branch is taken. For example, here at, P2 prime, you know two facts, that if V21B is less than 0, then V21F will be equal to 0. Okay. So, and similarly, if that is V21B is greater than or equal to 0, then V21F will be equal to V21B. And that's how, so that is the basis for which, how we ended up modeling it as a DNN, as a conjunction of these formulas. What we did was to make the strongest conditions, predicate that is expected to hold after each assignment statement, and then you put them all together into a conjunction of those each strongest post condition, and that's how you made up the model, the logical model for DNN. Once you did that, then you could express the query to verify. Okay, if under the input assumption and the model that you defined for the DNN, if the given post condition holds good. So you were able to express that as the whole verification thing as logical formula. So that is what was the basis. The basis for that was this concept of strongest post condition. So the strongest post condition here was quite simple because of this simple thing that there were no assignments. The same variable was not being assigned multiple times in your program. Okay, so so now I'm going to show you where this notion of strongest post condition kind of breaks down. Okay. Okay, take this example. You want me to make this bigger or can you read this font? Make it bigger, sir.
little bit bigger. Yeah.
So here is, say, an example that I have where the same variable is assigned twice. Okay. So after the first assignment, what I have in curly brackets here is what I call as the predicate that characterizes the precisely the condition that ought to hold good after the assignment is takes place. Okay. So here, since y is assigned to x, it was x is equal to y, so I'm asserting that x is equal to y as the strongest statement that I can make, okay, about the effect of executing the assignment steps. Here it is fine, right? Now, after when I reassign it, so taken that individually, of course, x will be x is equal to z. That logical statement is correct when that each statement assignment statement is viewed individually. But you cannot compose these things like we did for the DNN example here, correct? So if you did that, what will happen? You will have x is equal to y and x is equal to double equal to z. See, I'm using double equal here to distinguish between the assignment statement and the logical equality between the variables. Now, if x is equal to y and x is equal to z, as per the equality transitivity of equal, you will end up getting y is equal to z, which is actually not the case, correct? Because whenever you have multiple statements or you have things like a sequence of statements like this, where the value is passed around, that simple way of characterizing the strongest post condition will be logically unsound. Okay, what it is not, it worked for DNN because there was, the when viewed as a program that had that restriction that every variable there was assigned at most once throughout that program. It gets even, and therefore you need to change how you define a strongest post condition. Okay, so it gets even weirder. You can see, and if x is equal to x assigned x plus 1, then making the strongest post condition as saying x is equal to x plus 1 is simply nonsensical, right? Because x can never be equal to x plus 1. So the strongest post condition has to take into account the fact that what changes is it has to distinguish between the current value of x and the new value of that x takes for each of those statements. So the best you could say is something like this. Whenever you make an assignment y to x, what you can assert is that there exists some value which was held some value of y, say y naught, which is taken as the new value of x. Okay, and this is how it has to, to be completely accurate to capture the meaning of your of assignment statement. That's how it has to be stated. Okay, that there exists a y naught for which y, for value that is the initial value of y naught, such that, and after the assignment, x will become x1, where x1 is y naught. And it also captures the fact that the value of y doesn't change. It remains to be y naught. Similarly, so now you could start composing, okay? After you make the assignment x equals 0, you say it's the same thing. There exists some value of z. Okay, there exists some value of z, which is what is taken as the new value of x2. So effectively, what I'm doing here is that I'm time stamping the variables every time it changes, so that this the strongest post condition is stated in a in a sound fashion. Okay, this way of doing is that's how in Hoare logic you state the strongest post condition, and the effect of doing this is something like this. Okay, you remember that, yeah. So if you had x is equal to x plus 1, x is equal to x plus 2 as your program, and you want to prove something about x after these two assignment statements happen, one way of using this strongest post condition concept here is on the right side is to timestamp them. Okay, so at the beginning, your precondition is x is greater than y. So you're going to assume that. So you're going to timestamp them. So the x naught and y naught are the initial values, that x and y, such that x naught is greater than y naught. So after x is equal to x plus 1, x1 will be equal to something like x naught plus 1, okay, which is what the strongest post condition was. So each time you do that, and then finally, when you want to check the assertion, you have to check the assertion on the latest time-stamped version of those variables. Since x has been modified twice, your assertion you want to check will be x2 is greater than, if it is greater than y0 plus 3. The key takeaway here, the point that I'm making is here also the program is being modeled as a conjunction of sequence of strongest post condition that hold good individually after each assignment statements. And then you are, that's how the program is modeled. So the concept of strongest post condition is still used, and this existential quantification, because you can always choose why not to be something which is a new variable which can take any value. Okay, so when I say, when I am assuming x is greater than y, all I am doing is x and y can be any initial value, which is denoted by x naught and y naught, such that x naught is greater than y naught. And by time stamping, I'm distinguishing between, every time the value of that variable changes, because there's a new logical variable that I'm using to denote the value at that point at for each PC, effectively for each PC location. And that's how that you'll have to do. And this way of modeling that uses once again the concept of strongest post condition is called static single assignment. Okay, so of course there is you'll have to the number of variables that you need has increased here, okay? Because every time a variable is assigned, you have to introduce a new logical variable. So the number of variables are certainly increased. Number of time-stamped variables for each variable is has increased. That is as many times as the value changes, but still the program, because present day theorem provers like Z3 can handle millions of variables easily. And therefore, this way of modeling using timestamp variables is not impractical to for provers like Z3 to handle. Okay, and that's how it's done. Now, similarly, if you have conditional commands, then you will have to similarly introduce model each arms of the if then else. Okay, so for example, so this assignment x is equal to y is being done when under the condition x is greater than y. Okay, so here the initial assumption, you're not making any assumption about the initial values of x and y. But here, when you're executing the then arm of the if then else, you will be assigning x under the condition that x naught is greater than y naught. Similarly, this assignment x is equal to x is under the condition that x naught is not greater than y naught. So then you merge these two, once again, using another new logical variable, x3, which says that if under x naught greater than y naught, your value when I'm here after executing the if then else statement is x1, where x1 itself is defined as y naught. Okay, and so and that's how you do. And this once again is um, based on the notion of strongest post condition. So, what is the general rule for the strongest post condition? And that's what is stated here. Yeah. So, so this is how it is stated. So, if you start with any predicate that character, if your assignment statement is something x is what is being assigned, some expression e, which can involve in addition to any program variables including x, then if you're starting with a precondition characterized by px, then what the strongest post condition exactly states the new value of x. The new value of x is such that it includes every value of v that satisfies p, the predicate p, and the new value of x is the result of evaluating the expression e by plugging the value v to x. Okay, so this predicate characterized by the existential quantifier captures the set of all values can that are possible after that assignment is made. Okay, and that's what is characterized by this. So, for example, if you start with a precondition where x is greater than or equal to y, after you make this assignment statement x is equal to x plus 1, what you have is a situation where this existential formula is true. That is, x can be anything which is v plus 1, where for every value v that is greater than or equal to y, x will have a value which is v plus 1. Okay, so you can eliminate that existential quantification by saying by substituting an initial value for x, saying if x naught, say, which is x naught, which is different from x and y. So if x naught for any value x naught which is greater than or equal to y, x, the new value of x after this assignment, is such that x is equal to x naught plus 1. This itself will obviously imply x is greater than y, if indeed. So in that sense, this characterizes it completely. And this is what the strongest postcondition is. So what I've stated as existential quantification can be removed by instantiating that, by creating a new logical variables to denote the value in the pre-state prior to the execution of the assignment statements, and that's how you can eliminate existential quantification. Okay, and that's what is happening. And then you could uh, take the conjunction of all the strongest post condition after time stamping this value, and that is the basis for modeling in terms of SSA. Okay. Okay. So, any questions there? Okay. Let me then go back to full screen. Yeah, so that's what is done here on this simple statement here, and that's how so the model that we derived before was exactly doing this calculation. It was computing the strongest post condition, and here it was simple because it was all single assignments, so we didn't even need to time stamp them. Okay, of course there is so there is another notion. You can also do this in a backward fashion, okay? And the whole logic gives rules for doing proofs in a forward fashion, like I illustrated, and which is what was the basis for modeling programs as in SSA notation. You can also do it using the concept of weakest precondition, okay? Instead of starting with the assumption and then computing the strongest post condition after for each assignment or conditional assignment statements, you can do it backwards. Okay, and sometimes that'll work out even somewhat simpler. Okay, and here the idea is, suppose you want to verify that after you execute this program, okay, which denotes the DNN, that V31 should be non-negative, okay, should be positive, okay. Then you ask the question, what if I want V31 to be positive after executing this assignment statement, okay? What should be the weakest condition? That is, what is the set of all? What is a predicate? The weakest precondition characterizes the set of all values that V31 and V21F and V22F, which are the variables involved in this assignment statement, can take prior to the assignment statement, such that when after execution of this statement, P5 will be true. That is the question that's asking. If you are able to define the weakest such predicate that characterizes the set of all values which for each of which, when you execute this assignment statement, you will have this condition hold good. Okay. Now, it's kind of obvious, isn't it? Here in this case, since what is being assigned to V31 is the value of this expression on the right-hand side of the assignment statement, where the expression is evaluated as per the values that satisfy that are there that exist prior to that. And what is that? And that is exactly the value of this expression. So in order for if V31 should be positive here, it better be the case that this expression, when evaluated in the prior to that, this expression itself should be greater than the value of that expression should be greater than zero. Correct. Therefore, and that is how you could do. So that's exactly what the weakest precondition for an assignment statement is, that the value of this expression prior to the assignment statement itself must be greater than zero. For any such value, V21F and V22, any such valuation, it is guaranteed to be, because that is how the assignment statement behaves. Okay, and that's what the weakest precondition is. So here, so you could do that, and then you can use this concept repeatedly by computing the weakest precondition for every statement. Okay, so now you take P4 here and you propagate them across each of the arms of your if then else statement. Okay, so if P4 ought to be expected to be true here, then it better be the case that when you replace V22F, I mean replace V22F with V22B, okay, in this, that this expression minus V21F plus V22B be that's what is guarantees that after that you will have P4 to be true. Similarly, you do propagate P4 across the then arm, okay? And then here, since it is getting zero, so what you have is you replace V22F with zero, and then you get the condition that minus V21F must be greater than zero. And you then put them together by using a conditional formula, okay, which says that if V22B is greater than zero, then you better that then this condition must hold good, that you get the P3 prime, and otherwise P3 double prime has to hold good. And you can kind of do this all the way across until you get the entry point, and then check if your precondition is indeed implies your post the weakest precondition that you have derived at the entry point, which is P naught, and that's exactly and that's another rule of Hoare logic, which gives you the exactly gives you this how to calculate the weakest precondition for any predicate, and then you can reduce this proof of correctness into a like like in a calculus where you can repeatedly calculate the weakest precondition, and that's what this one is. Uh, so the weakest precondition rule for here I've stated here. Yeah. So here, this is the rule for a thing. So if you want P, some predicate P of X to be true after you make the assignment x is equal to e, then what the weakest precondition rule is saying is that it better be the case that the value of e be but the value of E satisfy P prior to the execution of the thing. Okay, so you whatever predicate that you take, you replace every occurrence of X in that formula that describes the predicate P by the expression E, and that is what that characterizes the set of all values that predicate characterizes set of all values which guarantee that this px will be true after the assignment, and that's what the weakest precondition rule is, and that's another way, a variation of how you could make proofs, and that's what was I intended to show here. So when for conditional statement, you can then combine this one. So if you have by decomposing, you first compute the weakest precondition for the two arms of your if then else statement. If they are WP of command 2, then if um, the weakest precondition for the if then else statement, where command 1 and command 2 appear as the then and else arm, is exactly this formula, okay, which is the conditional formula, which is what we used, okay. And that's another way to conduct the proof. So far, what we have seen is with these two things, what we have covered are the way to make proofs for straight line programs. Okay, can I straight line programs that have branches but no loops. Okay, so you can either do a backward proof using the weakest precondition rule, okay, in which case you propagate the post-condition statement all the way to the pre, or you can do a forward proof like we did here, okay, and you can take the precondition and then, I mean, you just make the strongest, model the entire program as a conjunction of all the strongest post-condition, and then you prove that the pre implies post under that modeling of the thing. Okay. Now, in the next class, what I will do is how do we do handle with loops? Okay, that is what I'm going to uh, discuss. And so before I end, so in this I will have uploaded this also. Now, I think what you need to do is, so if you see this one here, I have some examples, and I think I'll go through that. Okay, people who have taken, so here I've been, maybe I wanted to cover this first. Okay, so here generally I'm using predicates as characterizing a set of states. Okay, and you will have to be get comfortable with that. Okay, if you've taken a logic course, that probably comes naturally with you, naturally to you. Otherwise, you need to kind of switch between this notion of set, I mean a predicate which can be described as a propositional, I mean as a formula in first order predicate logic, as characterizing a set of values. Okay. And what I have here is some examples, simple examples that which when you review, you will get that idea. You will get familiarized with how to view formulas and predicates as sets. Now, for example, here the formula x less than or equal to 0 which defines px exactly denotes this set. Then when you take disjunction, it is like taking the union. Conjunction, when you take conjunction of these two formulas, it is taking like intersection. Where it gets a little bit hairy and requires some thinking is when you use existential quantification, like the way that I used in characterizing the strongest post condition. So, for example, when you take, suppose you have a relation Rxy defined by x greater than y. Okay. So this, I see these examples may look very pedantic for some of you who have taken logic courses. I'm going through them for the benefit of people who may not have had that luxury of having seen these formulas. So bear with me. Okay. So, if there is a relation defined as x greater than y, that's exactly the set of all values, a set of all instantiations, values that you can assign x and y. Here I'm assuming they're ranging over natural numbers such that I is greater than j. And that is exactly these set of pairs of values. Okay. And now, if you take an existential quantification, if you're asking the question, does there exist? What is, this set denoted by the predicate S2, which is ask the question if, what are the set of values for which there exists an X such that R of XY, then that one is like in all the values for which there exists y such that there exists an x such that x is greater than y. So this formula itself is now a predicate over a single variable, and it gives you all the values such that set of all values of x for which that value is greater than y. And you can see now that the existential quantification is like instantiating, enumerating all the values for which r of 0, y is true. So that's like taking a disjunction of all those values, and where a disjunction is a union. So in this case, it'll reduce to true. Okay. Similarly, S1 of x. So I encourage you to go through these things and convince yourself that indeed the way that I am defining predicate by existentially quantifying some of the variables out of certain formulas, indeed reduce to certain sets described by this closed form things, like I've indicated here. This is exactly what I was used to characterize the strongest post condition, strongest post condition by the whole logic rule. So, what the key takeaway here is, if some of you are not, yet comfortable with constructing formulas with existential quantification and understanding or viewing them as sets of values, then I encourage you to look at these examples and also work on assignment the zero, the DNN assignment there, where you will have to construct some specification involving quantifiers so that you get familiar, you get acquainted with quantifier, the use of quantifiers and understanding when, predicates are defined using formulas involving quantifiers, what exactly they mean. Okay. So there are no questions. I think I'll stop here. And um, any questions so far? Okay. I don't know if Shauriyam and Avik are still there. Okay. So they will communicate with you about setting up a slot for tutorial. And if you have any questions, And if you have any questions or doubts about this, the content of this lecture, please get in touch with Avi Consortium or me at any time, either during the tutorial or outside, and more than happy to clarify your doubts about this or about questions on the assignment. Okay. So I'll see you Wednesday at the same time again. Thank you.
Thank you.